Basics first. We've talked about initial value problems already, okay? But now we're going to start talking about higher order initial value problems, second order, third order initial value problems. And on the review sheet for our last test, one of the questions I gave you, it was kind of just I gave it to you on the review sheet just so that you kind of had a build up of what we're going to start doing here, was a second order initial value problem. And so, here, this is a linear differential equation. This is a higher order linear differential equation in that it's the nth derivative, so it's whatever that would be, it's bigger than 1. But the derivatives, if you look at all these derivatives here, including y, they're all to the first power. The coefficients out in front of each one of those, a sub 1, a sub n minus 1, a sub n, a sub 0, they're all functions of x, and this is a function of x on the other side, right? These are the criteria we had when we talked about something being linear. So we're going to try and solve these linears. All right, but it's an initial value problem, so then it's going to be subject to, and it's going to be giving us conditions. Now, it's going to need to give us more conditions the bigger the differential equation is. When it was a first order linear differential equation, all we had was really just this first condition, right? That was the only thing we needed. But when it's second order, we're going to need 2 different conditions. Third order, 3 conditions. Now, if you notice, the second condition that we're subject to is now using y prime instead of y. The reason being is, if you notice that each one of these conditions uses the exact same x value every single time. Okay, x sub 0, x sub 0, x sub 0. So remember, these are points, right? So if I plug this x value into the original function, I'll get a y value. Now, I'm not going to get a different y value because it's a function, right? 1x will give me 1y. So what I have to do is I then have to take that same x value and plug it into something else to get another condition. So I'll plug it into the derivative of the original function. And that'll give me another point, but that point is now on the derivative. And then I'll plug it into the second, the third, the fourth. So if you look at all these conditions here, the number of conditions you're going to need is always going to be one less than the derivative that you're dealing with for the order of the differential equation. All right. So if we're dealing with, say, a second order differential equation like we have right here, okay, let's look at this example. Second order differential equation. Okay. If I'm going to use this and do an initial value problem attached to this differential equation, I'm going to say it's subject to these 2 conditions, right? I need 2 conditions because I have a second order differential equation. Third order, I need 3 conditions. Fourth order, and I'm going to go up to the first derivative because I have the second derivative in my equation. Right. So if a question said find the solution to this differential equation subject to these 2 things, what would we do first? First thing we would have to do is find just the general solution, right? We'd have to find the solution to the differential equation, ignore the initial value part of it, solve the differential equation. That's always the first thing you have to do. The problem is this is a second order. Since it's a second order differential equation, we don't know how to do that yet, right? That's the whole point of this unit, is to learn how to solve these things. So let's just assume that we did know how to solve it, and this is the solution we came up with. And we're going to see where this comes from. Right? We're going to solve this exact same differential equation later in the semester. It's probably going to take us, not this week, not next week, the week after that. The week after that, we'll be able to build up to something like this and solving this, which seems like it's going to take forever to get there, but hey, we have to do it incrementally. All right. So anyway, let's assume we already solved it and we know this is the solution, right? Well, notice it has a C1 and a C2 in it. So if it has the C1 and C2 in it, we were going to need to solve the initial value problem, okay, given these 2 conditions, and use these conditions to help us find C1 and C2. Right? So all the work is generally done here for us in that they found the actual solution to the differential equation. Again, we have no idea how to do that yet. So let's, though, can we solve the initial value problem that's attached to it after we would have found the solution to the differential equation? And the answer is yeah. It's not that hard to do. We've seen that this is just a matter of plugging numbers in and finding C1 and C2. So let's go through this once we get some practice on how we do this with these higher order ones. So when the time comes, we'll be able to do it. All right, let's switch over to the whiteboard behind me. So, go. So again, we have this y double prime plus y equals, where is it? 4x plus 10 sine x. Okay. We have these solutions to this differential equation, which would already have been found. We'll figure out how to find that, okay, as we move through. But let's say we already found the solution. The solution is c1 cosine x plus c2 sine x plus 4x minus 5x cosine x. Okay. And we can check to see if this is actually a solution by doing what? This is y, so I plug it in for y. I would then have to find the second derivative of this thing, so I'd have to find the first and then find the second. Once I find the second derivative of this thing, I'd plug it in there, and this side should have to equal that side. And if it does, then this is a solution, right? We've talked about how to check to see if something's a solution to the differential equation. So let's just assume it is, right? They actually solved it. They solved it properly. They came up with this answer. So then what I want to do is I want to solve the attached initial value problem with the conditions of y of pi equals 0 and y prime of pi equals 2. So again, just use these two things to find C1 and C2. So this is saying I have this point pi comma 0, right, where x is pi and y is 0. And I could say this point should be on the graph of this function. Okay, what C1 and C2 would make that happen? So let's plug them in and see what happens. So if I plug y of 0 in here, and then I plug pi in for x, I would get C1 cosine pi plus C2 sine pi plus 4 pi minus 5 pi cosine pi. Okay. And so you should know that cosine of pi is 0 and sine of pi is -1. Okay. No, I have that reversed. Cosine of pi is -1 and sine of pi is 0. All right, so if sine of pi is 0, then that's 0, so that's just going to be gone altogether. This would give me what? Negative C1, because cosine of pi is -1, so negative C1 plus 4 pi. This would be minus 5 pi times a -1, so plus 5 pi equals 0. So quickly you see that C1 equals 9 pi. All right, so there, we got C1 out of this thing. All right, now we want to find the other constant too, and that's why we have another condition to help us find more constants. So if we were to do this, we would then have to plug pi in for x and 2 in for y prime. Okay? Y prime, because this is on y prime. This is not y. I can't go back to this equation and just plug pi in again, because it's just going to give me the same thing. It's the same exact x value I had before. So I have to plug pi into y prime and then 2 in for y prime. So pi into x for the equation y prime. All right. So that would require me to find y prime though. Well, I have to do that. It's going to be hard to do, find y prime on this thing. So let's write this over here. C1 was 9 pi. So I got y prime equals, where are we at here? So derivative, this would give me what? Minus C1 sine x plus C2 cosine x plus 4. This I'll need product rule, so minus 5 cosine x plus 5x sine x. And so I'm going to plug pi in for x and 2 in for y prime. So 2 equals negative C1 sine of pi plus C2 cosine of pi plus 4 minus 5 cosine of pi plus 5 pi sine of pi. Again, cosine of pi is -1. sine of pi is 0. So we got 0 there, that's all gone. This is -1, this is -1. So where are we at here? We got 2 equals -c2 plus 4 plus 5, because again, -1 and -5. Okay. So this is going to be 9. Bring it over here. So what we're going to get? C2 equals subtract 9. So what's that? -7. So 7 is your C2. So now we got C1 and C2. So then the solution to the IVP would be if we plug 9 pi in here and 7 in here. Okay? That's the solution to the associated IVP. Now that worked out pretty nicely in that we plugged in one thing, the C2s went away, we could just solve for C1. Then we plugged in the next one into Y prime, the C1s went away and we solved for C2. It's not always going to be that convenient. In that sometimes when I go to plug this in, so let's say I plug it into Y prime, I have something in here that has both C1 and so let's say C2s in it, C1s and C2s in it. Okay, so there's a C1, I'll just throw C1 in there. So it's the equation that has both variables in it. And when I did it in the first one, okay, when I plug this first one in here to Y, maybe I got another equation, I don't know, that had C1s and C2s in it still, okay? So the idea is, well, I still need to figure out C1 and C2 is, but what do I have? I have 2 equations with 2 variables in it. So I have a system of equations. So I can use some real basic algebra here, solve the system of equations, use elimination by addition, substitution, solve this for C2, plug it in there, or whatever. It should be pretty easy to do, but sometimes it's not going to be as convenient as like I had a second ago where, you know, you plug one condition in, you can just get one of the variables to show up, but the other one disappears, and the same thing. It's not going to work out that way all the time. But nonetheless, all you're doing is just plugging things in and solving for C1 and C2. Here you're plugging it into Y. This one tells me I'm plugging into Y prime. And that's really the key there. All right. Questions?
Nope.
All right, let's keep going. So then we have what's called a boundary value problem. Okay. So now in a boundary value problem, things are a little different. We're not going to do that many boundary value problems, and oftentimes in this first semester differential equation, boundary problems are skipped over altogether, but it's not hard to throw this in here, so I like to just cover it just so you have an idea of what it is. So anyway, boundary value problem starts to look pretty much the same way. If you look at, say, this second order differential equation, it doesn't have to be second order, but here's a second order linear differential equation, right? Where the highest derivative is only a second derivative, rather than giving you just the whole general one. And then we have a subject 2. Okay? So it looks a lot like the initial value problems. This right here is what we call a boundary value problem. Solve this differential equation subject to these conditions. But take a quick look at the conditions. Look at the x values. Unlike the last one, where pi was the x value in both cases, notice this says x sub 0 and x sub 1. In which case they're choosing a different x value for each condition. Well, if you choose a different x value for each condition, you don't then have to jump to y prime, right? You can continue to work with the original function. You could choose to jump to y prime if you want the next condition to be on the derivative, but you don't have to, right? So the big difference between a boundary value problem and an initial value problem is the conditions and whether or not you continue to choose the same x value, in which case you're going to have to move to a different function, y prime, y double prime, y triple prime, whatever. Or a boundary value problem where you can choose different x values for each condition, and therefore you could stay on the same function all the time. So if you notice, it's y in both of these. It's not a typo where I forgot to put the prime on there. It's specifically not y prime because it's a different x. Okay, so we're basically saying this is a point on y, and that point is x sub 0, y sub 0. That's on y, and this is another point that's on y as well, and that's x1 and that's y1. Okay. And when you make that little change, we change it from what we call an initial value problem to a boundary value problem. The way you do it is not really that much different. So that's why sometimes this is skipped over in first semester DiffyQ class, but it's so similar that it's really not a big deal for us to cover it now. Okay. Now the problem is finding a solution. You're less likely to have a solution to this boundary value problem than you are to an initial value problem. And the main reason is I have to find a solution y that not only goes through this one point, but goes through both of these points at the same time, right? So we talked about how we have like a family of solutions where you have a bunch of different graphs representing all the different solutions to a differential equation. And we said, we want to find the one member of the family that goes through that point. And once we find that one member of the family goes through that point, then that's the solution to the initial value problem. Now we're saying, what member of the family goes through that point and this point at the same time? Well, what if this one point is here and this other point is over here and all your graphs look like this? Well, you're not going to find it, right? So these don't have solutions as nicely all the time as the initial value problems necessarily. So that's another reason why we don't do it a whole lot right now in this beginning part of differential equations. But anyway, if we look at an example, let's solve this differential equation subject to these two conditions. Notice the two conditions have a different x value in each condition so that we can use y in both of them. Now we would have to first be able to solve this differential equation. That differential equation is a second order differential equation. We don't know how to do that yet, right? We've only solved first order differential equations. So let's just say we knew how to solve it, and this was the solution we got. All right, so there's the solution. How it comes about, we'll figure that out next week. By next week, we'll be able to come up with this solution, okay, to this different. There's something very specific about this one that's different from the last one. That's a little bit easier to solve. So we'll be able to solve this one by next week. We'll come up with this solution. So let's just assume we know it. Let's solve then the initial, or in this case, the boundary value problem that's attached to it, right? Can we find what C1 and C2 are based off of these two conditions? Right. So let's look at it. I'll do it on the board again. Okay. Let's see. All right. So we got y double prime plus 16y equals 0. And we got the solution they already found for us, which was C1 cosine 4x plus C2 sine 4x. Right? Yep. And we got these conditions subject to y of 0 equals 0. And y of pi equal, or pi halves equals 0. Okay? So, find C1, C2. Again, plug them in, right? This is telling me I have this point 0, 0 on y, and this is telling me I have this point pi halves comma 0 on y. Okay? That's all. That's all that's doing. All right, so let's look at the first one. If I plug 0 in for y and 0 in for x, what happens? I get 0 equals C1 cosine of 4 times 0 plus C2 sine of 4 times 0. 4 times 0 is 0, so I have to know how to do the cosine of 0 and the sine of 0. Well, cosine of 0 is 1, sine of 0 is 0. Well, sine of 0 is 0, that's gone. So this tells me I have 0 equals C1 times 1. Well, that tells me that C1 has to equal 0. Okay? First part. Second one, pi halves 0 in. So if I do that, I get 0 for y, C1 cosine of 4 times pi halves plus C2 sine of 4 times pi halves. Again, 4 times pi halves would be 2 pi. So sine of 2 pi, cosine of 2 pi. Well, that's the same thing as 0, actually, right? The sine of 2 pi is 0. The cosine of 2 pi is 1. So what happens here is the same thing again. I get 1, and this thing's 0, so I get C1 equals 0. So I didn't find a C2. This is a problem with boundary value problems, right? I can't find a C2 from these two conditions. So what we would say is, all right, well, we just don't have a solution to this one, right? We don't have a solution to this boundary value problem. But if we could, it would be nice if that one would have gave us another solution. So probably if I change this condition a little bit, maybe we could come up with a C2. Maybe if I put like pi instead of pi halves or whatever. But anyway, this is the problem. We don't have a C2, so we don't have a solution to the boundary value problem, right? So this is the issue with it. But if you notice, it's not a whole lot different here, right? The big difference is this, but how we do it is just plugging things in, finding our constants. The big question is, how do we come up with the solution to the differential equation? That's where we're going to spend our time. But it doesn't hurt to mention this idea. All right. So let's go back to the PowerPoint. Again, last time I'm going to say this, I've said it a bunch of times. Big difference between IVP and BVP, okay, is are we using a single X value over and over and over again, or using multiple X values for each condition? We'll primarily stick with initial value problems. All right, so let's get into now what we really want. So again, this whole thing is just intro of what we're going to need over the course of the next unit. And one big thing we're going to need to talk about is linear dependence versus independence. Some of you already have a concept of this from other classes. If you're in linear algebra or have had linear algebra already, I'm sure you've already talked about linear dependence and independence. But if not, you know, we're going to talk about it now. All right. So set of functions f1, f2, f3, all the way up to say fn is linearly dependent. Okay, these functions are linearly dependent on some random interval. Okay, if there exists a c1, c2 up to say cn, not all 0, that's a key, such that this linear combination equals 0. A linear combination is when you multiply each one of these functions by some constant and add them all together. Okay, so c1 times f1, c2 times f2, c3 times f3, all the way up to cn times fn, all added together equals 0. Okay, if that can happen, if there's a set of constants for which we can make this happen, this linear combination equals 0, then those functions are considered to be linearly dependent. If not, then we say that they're linearly independent. Now, this not all 0 is pretty key, okay? Clearly, if I made C1, C2, C3, all of those 0, right? If every single one of these was a 0, then I multiply each function by 0 and add it all up. Clearly, it's going to give me 0, right? So not all of them can be 0, but some of them can, right? So let's say, I don't know, C2 is 0, but not C0, not C1, not Cn, right? But still I can find a bunch of these constants so that I can get it all to 0 itself out. That's okay, right? They're considered linearly dependent. But not all of them can be 0, because you could do that for any set of functions. You could find any set of functions where you multiply every single one of them by 0 and add them together, of course you're going to get 0. Right? But again, if we can't do this, then we say that they're linearly independent. So, you know, this is the basic idea that we're looking at. Another thing to note here in this is that if we look at a set of functions, f1, 2, 3, up to fn, we could say that they're linearly dependent on some interval if at least one function can be expressed as a linear combination of the remaining. Because that means that we could take all the functions somehow and cancel them all out with some random constants. So if you can get a bunch of the functions to be a linear combination of the other, we can just multiply it by a negative and then they'll cancel each other out and get you 0. All right, so let's look at a couple examples. So I thought I had another example here. Let's start with this one. All right. So look at these two functions, f1 and f2. Are these functions linearly independent or dependent? Well, you know, you have some experience with these types of functions already. So you can determine whether they're linearly independent or dependent simply just by looking at them, okay? That's not the greatest way to do it, right? But is there a C1 that I can multiply by F1 and a C2 that I can multiply by F2 such that this combination would give me 0? And C1 and C2 can't both be 0. Well, since there's only two of them, neither of them actually could be 0, right? Because if one of them's 0, then the other one would have to also be 0. So anyway, is this possible? Well, you should recognize a little bit about these functions, and if you mess around with it a little bit, there's some trig identities we could use. We could easily find that this is definitely going to work because these are going to be linearly dependent. Now, telling you just to mess around with it to try and find something is not the best way to do this, right? We're going to come up with a better way to get this done to determine dependence or independence. But in this case, if we just mess around with this a little bit, one thing you have to understand is that there's something called the double angle identity. That sine of 2x equals 2 times the sine of x cosine x. And once you have that, you can realize that, yeah, I'm going to be able to make this work. Because if I take C1 to be 1 and C2 to be -2, I'll easily be able to get these two to cancel out. Neither of these are 0. If I take 1 times f1, which is sine 2x, plus -2 times f2, which is sine x cosine x, what are you going to get? Well, remember, this is the double angle, which this is the same thing as 2 sine x cosine x minus a 2 sine x cosine x. They cancel each other out, and clearly you're going to get 0. So was there a C1 and C2 not equal to 0? Both of them, you know, in this case, not equal to 0, such that we can make this linear combination 0 itself out? Yeah. So what are they? They're linearly dependent. Pretty easy one. I think anybody who messed around with this enough would be able to come up with that one. Again, they're not always going to be that easy. And what you're not going to want to do is just say, let me mess around with it till I can find an answer. But just to get comfortable with it, we'll do a couple like this. How about these two? G1 and G2, are they linearly independent or dependent, right? So is there some C1 times x squared plus C2 times log x that I can make this thing 0 itself out? Well, the key in the last example was that they're related functions, right? In that, you know, the sine 2x had a double angle identity that was related to the other function, which was sine x times cosine x. So there was a way we could get them to cancel each other out. Big question here is x squared and log x at all related, such that there's a constant multiples here that'll make them cancel each other out? And working with these functions enough, you've been doing it for years, right? I mean, ever since you started talking about these types of functions back in algebra, you've been dealing with x squareds and log x's, etc. Dealing with these things as long as you have, you should probably think that there's no way I'm going to be able to get these to cancel each other out by multiplying by just some random constants where they're not both 0, okay? So in this case, they're independent. But there's no real way I showed that, right? I'm just using my intuition to say that I know x squared and log x have no relation whatsoever. There's no way I can write one in terms of the other one, right? That's what we did with the last example. We wrote one function in terms of the other function so that we were able to get them to cancel each other out. There's no way I can do that for x squared and log x. I just know that from working with it. But that's in no way a proof to show that they're independent. It's one of those things I can just say, I know it, right? Which is a horrible thing to say on a test. How do you know the answer? I just know it, right? So we're going to have to come up with a way to actually do this, right? And we're leading up to it. Just give me a little bit more time. All right. The more functions you have, the harder this will be. But remember, some of these constants could end up being zeros, right? So as long as all of them aren't zero, then that's all that matters. So if you look at this one here, I got 4 functions here that I need to combine to decide whether or not I can get this linear combination to zero out or not. More functions, more work. It's going to take longer to do this, but is it possible, right? Is there a C1 times H1 plus a C2 times H2, C3 times H3, and a C4 times H4? Okay, that'll zero this out. And you start to see there's some relationship between some of these functions, right? So I think if you played around with this thing enough, you might be able to get this to work out. And so let's do this. Let's say, what is it? C1 is, let's go with 1 for C1. Let's say this is square root of x plus 5, right? That's C1, that's H1. And then in order for that to cancel out, I'm going to need this square root and this square root to cancel each other. So I'm going to say C2 is -1, right? That way I'll get it to cancel out. So that'll be square root of x plus 5x, right? So now what am I going to have? I'm going to have a square root of x times 1 and a square root of x times -1. That at least cancels those two pieces out. I got a 5 here, and this is going to be a -5x. So now we got to go a little bit further to try and get that one to work out. So if I multiply this by 5, so that's x1 minus 1, this will be a 5x, and that -5x will cancel. And this will be a -5, and this +5 over here will cancel. So now I got everything zeroed out. So let's say just C4 is 0 times x squared. And there we go. It's all going to zero out. Again, this will be square root of x plus 5. This will be minus square root of x minus 5x. This will be a 5x minus 5. And then this will be a 0 equals 0. Again, remember, all this is going to cancel out. So I just kind of build it as I went. These cancel, these cancel. So yeah, I got it to zero out, linearly dependent. But that's because I noticed there's so much relationship between all these functions that I should be able to make it work. But again, I'm just messing around with it, right? Not a great way to do it. So that's where we're going to come into this next thing that's going to say, this is a systematic way of determining whether or not your functions are linearly independent or dependent. And this is going to be important for us because this is all about solutions to differential equations. So there's this thing called the Wronskian. And the Wronskian is basically the determinant of a matrix. We need to talk a little bit about determinants of matrices, which you should have some experience with already because Calc 3 you did cross product. Okay, and those people who are currently in Calc 3 right now, we've already covered cross product, so you know you have that already. And so cross product is the determinant. Okay, it's the determinant of a 3x3 matrix, and that's basically you know where we're going to go with this thing. We could go higher, but we're not going to go higher than 3x3. So anyway, Wronskian. So if we're looking at a bunch of functions and we want to determine if they're linearly independent or dependent, what it says is, let's look at these functions. Let's line them up across in a row. However many there are, it doesn't really matter. We're not going to go above 3 because you know anybody who's worked with determinants, you know, in depth knows that the bigger this is, the harder it's going to be. We won't go beyond 3. And so if I look at these, let's line these up across this row. So however many there are, we have to create a square matrix. So then I'm going to have to make this the same amount of columns as I have rows. So let's say I have 3 functions, F1, F2, and let's just call this F3. So that means I have 3 columns. I'm going to need 3 rows total to make this square. So then the next row would be the derivative of each one of those functions. And the next row would be the derivative of that. So now the second derivative. And I'm going to keep going until I make this a square matrix so that I can find the determinant. So if I had 6 functions, I'd have to go all the way down to the 5th derivative. Remember, this is the first row, so I need to go to 5 rows total. First, second, third, fourth, 5th derivative. So 6 functions, 5th derivative would I go down to. Anyway, once I get this square matrix here, if I find the determinant of this matrix, which we're going to call the Wronskian, and we're going to use this notation, capital W of the functions, right? The Wronskian of these functions. I'm going to find that, okay? Whatever that is. I don't know what that was. Everybody okay?
I'm good.
I'm good.
Right?
Yeah, I don't know what that was.
Okay, all right. So anyway, once we find this Wronskian, right, this will tell us whether or not our functions are linearly independent or dependent. Now, why is this important? Because what we're really interested in is linearly independent functions. Because these functions are actually going to end up being solutions to differential equations. And so when we find solutions, we only want the solutions that are all linearly independent with one another. If 2 solutions are linearly dependent with one another, they're not considered to be different solutions. One's just basically a multiple of the other. So they're not going to be 2 separate solutions. They're all just going to fall under the same solution. So ultimately, as we do this, we're going to be trying to find solutions of differential equations. These are bigger differential equations than what we've done so far. There's going to be multiple solutions. The only solutions we're going to be concerned with are all the solutions that are linearly independent, okay? Independent solutions. And so I could say, let's try and figure out if these solutions are independent by just messing around with them, which is not great to do. Or I could say, we can really determine if all these things that we just found are independent by calculating the Wronskian of those functions, okay? And so the idea here is, if the Wronskian is not equal to 0, okay? If I look at all these functions and I find the Wronskian, and the Wronskian is not equal to 0, okay, then the functions are linearly independent. So that's what we're going to want. So let's look how we can calculate this with a couple examples. All right, so here's 2 functions. And rather than trying to mess around with them and turn one into the other, or get one to multiply by something to get to the other one, right? See that they're multiple of each other. We could simply just plug these into that Wronskian, find the determinant of that matrix, and right away it'll tell us they're independent or they're dependent. All right, so let's look at this example. So F1 is sine squared, right? Is that what it says? Say it's sine squared, and F2 is 1 minus cosine 2x. Again, you could use just what you learned in trigonometry and mess around with them, see if one can be turned into the other one, some form of the other one. But if we simply just create a matrix, sine squared x, 1 minus cosine 2x. I have 2 functions. So I need to create a 2 by 2 matrix so that this is square. So that means I only have to find one derivative for each one, and now I'll have my 2 by 2. The derivative of sine squared, 2 sine x cosine x. Chain rule, outside comes in, this power comes out to the outside, new power is 1, inside stays the same, multiply by the derivative of the inside. Derivative of this function over here, 1 would be 0, cosine 2x would be, what's that going to be? It's going to be 2 sine 2x. Okay. Derivative of cosine is minus the sine, so it'll cancel the minus. Inside stays the same, then derivative of the inside is 2. All right, so now we have this, we don't find the determinant of this matrix, and that's going to be our Wronskian. Now, if you remember 2 by 2 matrix determinants, A, B, C, D, okay? It's the easiest determinant you could possibly find. This times this minus this times this. So A times D minus B times C. That's it, right? So I'll do this times this minus this times this, and we're good to go. So this is going to give me sine squared x times 2 sine 2x. And then this will give me 2 sine x cosine x times 1 minus cosine 2x. It's not clear whether or not this does or doesn't equal 0, so we got to mess around with it a little bit. One thing we can do is we can say, well, this, we can do a couple of things. Let's look at sine 2x and this 2 sine x cosine x and say that they're really basically the same thing, right? Because we talked about that double angle identity, that sine 2x is equal to 2 sine x cosine x. So if they're the same, I could factor that out, and I'd be left with sine 2x is going to factor out. Okay, I have 2 times this still, which is 2 times sine squared. And this is gone, so then I have plus 1 minus cosine 2x. Okay. All right, we'll go a little bit further here. Okay. We'll go a little bit further. This is another double angle identity, which you're also going to need to know for this one. So cosine 2x. All that is cosine squared minus sine squared x. So we're going to use that. So what do we have here? We have sine 2x times 2 sine squared x plus, this is going to be a 1, minus this. So minus this, I'll have a negative cosine squared plus sine squared. Okay. Okay. What next? Oh, let's do this. We're going to take this and we're going to write it as sine squared plus sine squared. Is that going to help? I just did this one. I can't remember what I did. No, that's not what I wanted. Oh, here we go. I'm going to write this. I feel like I'm missing something here. What am I missing? I'm going to go a different way with this one. There's another double angle identity here. And it has to do with sine squared. So I can continue on with this, but I can give you this other version. What do you know sine squared? Sine squared, we know that sine squared plus cosine squared equals 1, right? So I could also look at this and I could say this is the same thing as 1 minus sine squared minus another sine squared is going to give me 1 minus 2 sine squared. So I'm going to use that instead. Okay, it's going to get through this a little bit quicker. So if we did that here, rather than do that, there's a couple of different versions of the double identity for cosine. I used the wrong one. We're going to use this one. So this is going to be 1 minus 2 sine squared x. Okay. Now with that negative distributed in there, now we're all good to go. I feel like that negative is still in the wrong spot. Come on, guys. You got to unmute yourself when you see me make a mistake here. What did I go wrong? Anybody see the mistake? Someone unmute it and correct me. I'll give you an extra point on your test. What?
Never mind.
You added when you did the determinant instead of subtracting.
Good. Who are you? What's the name? Sorry, I can't see my names right now on my screen.
Ryan Petstilla.
All right. You're getting 1 point added to your last test. That should be a minus. Ryan, let me write this down so I don't forget.
I definitely said the sign, but
You said it too?
I said it, but I wasn't sure of myself.
All right, who's this? Who's talking?
Raj.
All right. I'll play it back, and if you said it, then I'm going to give you a point too. All right, anyway, the mistake was, I knew it worked out when I did it just a couple minutes ago. Anyway, my mistake was you do this times this minus this times this. So there should be a minus there when I do this. Now that changes a lot because there's a minus here, which there's a minus here, okay? So then this becomes a plus because this distributes in here and here. So -1 and this becomes a plus. Now that that becomes a plus, this works out really nicely because then look what happens. I have a 1 and I have a -2 sine squared. So -1 plus 1 cancel, 2 sine squared minus 2 sine squared cancel. Well, if all that stuff cancels, what do I have? I have sine 2x times 0, which is 0. Okay? That took way too long to get through something that we shouldn't have taken that long to get through, but it's because I made a mistake. Anyway, that tells me that the Wronskian of these two functions, sine squared x and 1 minus cosine 2x, is 0. And if the Wronskian is 0, then they're not linearly dependent. Right? Sorry, they are linearly dependent. They're not linearly independent, is what I should say. Okay? So these are linearly dependent functions. So why is this all significant? It's all significant because if these were two solutions I found to a differential equation, I wouldn't treat these like two solutions. Okay? These would be the same solution over again. So it's worthless for me to have both of them. I only really want one of them. But if they were linearly independent, then I would keep both of them as separate solutions. Okay? That's the whole significance of this thing. All right. Let's go to another one. Anybody have questions on that?
Nope.
Come on. All right. This is going to be a pretty important one. So let's look at these two functions, okay? And decide whether or not these two functions are independent or dependent using this Wronskian. So e to the m1x, e to the m2x. m1 and m2 are just some constants, but they're not equal to each other. Because if they were equal to each other, and I did c1 e to the m1x plus c2 e to the m2x, I'll definitely be able to get 0. If these are both equal to each other, then essentially these are the same function. And if they're the same function, then I just make one of these things +1, one of these things -1, and I can easily get them to cancel out. So, you know, that's a silly example. So let's assume that they're not equal to each other. So these are two different exponential functions. say something like, I don't know, e to the 3x and e to the 5x, right? Are these types of functions linearly independent or dependent? Again, if we just do the Wronskian between these two things, we could easily see whether or not the Wronskian is going to be 0 or not. And if it is, they're dependent. If not, they're independent. So let's do that one. Again, since it's only two functions, it's only a 2x2 determinant that we'll have to do. So computationally, not too bad. If we got up to, say, 3 functions, now so it's get worse. But so we have what, G1 was e to the m1x, and G2 was e to the m2x. So e to the m1x, e to the m2x. So derivative, I only have to do one derivative for each one to get this to be square. So I'll have just m1 e to the m1x and m2 e to the m2x. So then I'll do this determinant, this times this minus this times this. I'll make sure I do the minus this time. All right. So what do we get here? I'm going to get m2 e to the m1x e to the m2x minus m1 e to the m1x e to the m2x. They both have an e to the m1, e to the m2x, so I can just pull that out. E to the m1x, e to the m2x. I can even combine that into just one exponential, but not necessary. Then I have m2 minus m1. Now, a couple things you got to remember about exponential functions. One, an exponential function on its own, that'll never equal 0, regardless of what m1 is, right? No matter what m1 is, this exponential function won't equal 0. It's always positive. So that never equals 0. That never equals 0. Well, what do we have? We have 3 things multiplied together equal to 0, right? In order for that to equal 0, one of those has to be 0. Basic principle of algebra, right? It's called the zero product property. It's how you solve equations by factoring. So the idea is that one of these things has to equal 0. We just said that never equals 0. That never equals 0 by the fact that they're exponential functions. So the only way this thing could equal 0 would be if this equals 0. Well, the only time m2 minus m1 could equal 0 would be if m1 and m2 are equal to each other, right? If m2 equals m1, you simply solve this, right? Plug m1 into the other side. That's the only time it's going to happen. But we said from the beginning that m2 does not equal m1. We're not looking at that scenario because if m1 and m2 were the same, these would be the same function. And of course, they could be a linear combination of each other. That it zeroes itself out. So since then, basically what we're saying is, well, this doesn't happen. We're also saying that this never equals 0. Well, if none of these ever equal 0, then by default, this could never equal 0. Okay? Because remember, you have a bunch of stuff multiplied together. If that's going to equal 0, one of them has to. But we just went through and said, that doesn't, that doesn't, that doesn't. Okay? So if none of them ever equal 0, then the product could never equal 0, which tells me that the Wronskian is never equal to 0, which by default tells me that these two functions are linearly independent. Okay? Linearly independent functions. All right? So if I have a solution to a differential equation, that is, say, e to the 3x, and I find a solution to the differential equation again, and I find another solution to be e to the 5x. M1, M2. 3 is my M1, 5 is my M2. Then what I'm telling you is that these will be treated as two completely different solutions because they're linearly independent. That's going to be pretty key because we're going to find solutions to differential equations that look exactly like that. And since we've already proved that they're linearly independent, we won't have to go through and prove it later. okay, we're already going to say, well, we know that these types of functions are linearly independent for one another. We did it. Okay, done. Don't have to check it again. I don't have to check it for these two specific ones because I did it really generally up here with just calling them M1 and M2. Okay, but we'll treat these as two completely different solutions. So now we have two solutions to a differential equation if we were able to come up with these. All right. So anyway, the Wronskian is basically a more systematic way of determining this independence. Rather than just saying, let's mess around with it, see if we can find something. So if we went back to maybe that example that I did earlier with the x squared and the log x, same deal. Like I just said, well, I know they're independent because I know, right? I mean, it's just, I know these two functions. I can figure out they're independent. But if I use the Wronskian for those, I can prove that they're independent. Right? I'm going to set up the next one. We're not going to do it. I think we're kind of short on time today. So I took too long on that one example. But it doesn't matter if we do this or not. So this example here, more of the same. It's only two functions. Okay. Take note, though, I'm just going to tell you off the bat, these are going to be, oh, I went too far. This one. These are going to be independent as well. So just look at this. We talked about the two exponential functions as long as these things are not exactly the same, being independent. But now if you look, I'm saying this is both alpha and this is alpha. So they're exact same exponential function. But if I multiply by cosine beta x or this one by sine beta x, I'm now creating a situation where these are actually going to end up being independent. So I'm not going to do this one out. Just remember this. Take note, put it in your notes, whatever, that e to the alpha x cosine beta x and e to the alpha x sine beta x are independent, linearly independent functions. Because the reason why I just want to point this out is we're going to find solutions to differential equations next week that look like this, okay? And when they look like that, we're going to say that they're linearly independent. Why? Because I told you they were. We should have just did the example right now and do a 2x2 matrix, but we're not going to do that, okay? You're just going to believe me. They're independent. Here, this one is one I want to spend a little more time on. Again, we're not going to do this whole thing, but I want to spend a little more time on it because this is three functions. So here's another one. They're going to be independent. Okay, these three are going to be independent with one another. But I just need to show you how to do the Wronskian with a three-function set. So same deal. We're going to create a determinant, but in this case, we have to create a 3x3 determinant. So computationally, this is going to take a little bit longer. And this one's going to get pretty messy real quick, but nonetheless, we're going to do a 3x3 matrix for this thing. And just review how you do the determinant of a 3x3. But in the end, this is going to be independent as well. And same deal. We're going to find solutions that look like this as well. All right. So anyway, let's look at this one. Just so you have an example of a three function one. So I got z1 is e to the x, z2 is x e to the x, z3 is x squared e to the x. Okay? So if I started creating my matrix, e to the x e to the x squared e to the x, in order to get this to be square, I have three columns. I'm going to need three rows. So I'm going to find the derivative of each one and then the second derivative of each one. All right, so I'm going to have to go down to the second derivative here. So this will just be e to the x, and then e to the x again will be the second derivative. Not a problem. Here to find the first derivative, I'm going to need product rule. So product rule is going to give me e to the x plus x e to the x. Okay, derivative of x is 1, and the derivative of the x is e to the x. Then I'm going to take the derivative of that again. Okay, well, derivative of this is going to be e to the x. The derivative of this is going to need product rule. Well, I just did that, right? The derivative of that is this whole thing. So I'm going to have an e to the x for this one, and then the derivative of this one's going to be this whole thing again, which is going to give me another e to the x. So I'm going to say 2e to the x plus x e to the x. And we get this one. Again, product rule. So I'm going to get 2x e to the x plus x squared e to the x. That's your first derivative. Second derivative, I'm going to need product rule for both of these. And you see this is going to start to get pretty extensive. So product rule here is going to give me what? 2 e to the x plus 2x e to the x. Then the product rule for this one, well, that's the derivative we just did because that's this function, so that's this whole thing. So that's 2x e to the x plus x squared e to the x. Well, these are the same, so I could write that to condense it down to 4x e to the x. I know we get that. All right, so now I got to find the determinant of this 3 by 3. So again, it's just like cross product back in Calc 3, right? Cross product's the 3 by 3 determinant. We got our I, we got our J, we got our K, right? And so the idea is we would take this term, whether we call it I or call it e to the x, doesn't matter, and multiply it by the determinant of this 2 by 2 matrix. Well, you see, with this example, the computation is going to be pretty crazy, right? This times this minus this times this. But, you know, you sit there and do it enough, you can do it, right? It's just time consuming to multiply all that out. So that determinant, but that whole thing then has to be multiplied by an e to the x. Okay? Then we have, this is my j, and that'll get multiplied by this, and this is 2 by 2 determinant. Okay? So this times this minus this times this, that determinant times this one. And then the third one, which is my typical k, and this 2 by 2 determinant over here. And then you can see this thing's just going to take pages and pages to do this whole thing. But in the end, does it give me 0 or not? Okay. A lot of these are similar pieces, so as you start multiplying them out, you're going to see certain parts cancel each other out, and they're going to start going. But in the end, what you're going to get to is it's not going to equal 0. Okay? This is going to take us a half hour to get through, which I don't have a half hour of time to do to get through it. Just knowing that, you know, I wanted to set one up for you just so you kind of see how it would work of the 3 by 3 Wronskian. But anyway, this one's not going to equal 0. So that tells me that these three functions are also going to be linearly independent. So if we ever come up with solutions to differential equations that look like that, so take note of it, that, okay, if this happens, we'll know because Mr. B said that they're linearly independent. And we can check it, like I said, on your own, you can go through and check these. And these are in the book, so you can see the book checks them too. But, you know, they're going to be linearly independent. So let's get to the whole solution part of this thing. So the whole idea is that these functions are not just some random function. These functions are going to be solutions to differential equations. But we've got to talk about two different types of linear equations, homogeneous and non-homogeneous. Okay? Now, the homogeneous I'm talking about here is not the same homogeneous we dealt with in the previous chapter. The previous chapter, we talked about homogeneous having this property of a function where that when you plugged in tx, ty, you got basically the original function back again times a power of t. This is totally not that. This has nothing to do with that, right? So, you know, students every semester kind of joke that, you know, we can call one of them homogeneous and the other one homogeneous, okay? I mean, it doesn't really matter. You should be able to recognize the difference between them. So anyway, homogeneous. If I took a linear differential equation, okay, that's what this looks like on this side. If I took a linear differential equation and on the other side, that function of x was specifically 0, okay? So all the same things we need for a linear differential equation, right? All the derivatives are all to the first power. The coefficients in front are all functions of x. But this right-hand side was specifically equal to 0. We're going to call that homogeneous. Okay? So that's what the new homogeneous means for linear. It's a type of linear differential equation. If it wasn't equal to 0, if it was equal to some random function of x, that's going to be non-homogeneous. Okay? Again, this has nothing to do with the type of function that we called to be homogeneous before. So if you look at these two differential equations right here, the left-hand side on both of them, it looks exactly the same. The right-hand side, one of them has an x, the other one has a 0. So this is the homogeneous, this is the non-homogeneous, but they're related to each other. And so the idea here is we're going to actually need to solve both of them. We will first solve the homogeneous one. Okay? We're first going to solve this homogeneous one. And then we're going to use the solutions of that to solve the non-homogeneous one. So that's why we call this the associated homogeneous to the non-homogeneous differential equation. So one thing we see when we do this whole unit is we incrementally start building more and more and more to finding solutions, and they start getting bigger and bigger. So we start off with the smallest, which is the homogeneous equations. They're going to be the easiest ones for us to solve. But then we're going to use all that information to build on to then solve the associated non-homogeneous. Okay? And this is something I talked about last chapter. If you remember, during the linear differential equations lesson, I said, look at the solutions that we're getting and look at the original differential equation. Notice this differential equation is equal to 0. Look at the answer we get. Notice this differential equation is not equal to 0. Look at the answer we get. And I said that over and over and over again when we're solving the linear first order differential equations. This is where it's coming in, okay? Because we're either solving one that's equal to 0 or not equal to 0, and look at the answer that we get. And how when it was equal to 0, we just got the one piece that had a c attached to it, and that was it. And when it wasn't equal to 0, we got multiple pieces, one that had a c and one that didn't have a c in it. This is where it all comes together. This is why I kept saying it over and over again in the linear lesson. All right. Before we get quite to there, okay, if we just look at the homogeneous ones for right now, the equal to 0 ones. If we find a bunch of separate solutions to the differential equation, the homogeneous differential equation, y1 is one solution, y2 is another solution, y3 is another solution, and they're all linearly independent, then what we're going to say is that the linear combination of all those solutions is also going to be a solution to the differential equation. So we're going to take all those little solutions, all those individual functions that each solve the differential equation, and we're going to combine them into one giant solution where we take the linear combination of them, which we know isn't going to equal 0, right? That's not going to equal 0 because they're independent. That linear combination of all those solutions is going to be what we call the general solution to the differential equation. So we're going to combine all of them into one solution, okay? We could call all these solutions the fundamental set of solutions. It doesn't really matter. What we really care about is when we put them together, we get what's called the general solution. That's the most important part. So like I said in the last example I had up there previously, if I find that, say, one solution to the differential equation is e to the 3x, and another solution is e to the, say, the 5x, okay? Then I can say that c1 e to the 3x plus c2 e to the 5x also solves that exact same differential equation that these both individually solve. And why can I say that? Because this whole thing could solve the differential equation because I could get both of the individual ones at once. If I let c1, which is just some random constant, be 0, then what do I have? I just have this, which is this solution, right? And if I let C2 equal 0, then this one would pop out. But also then I can have the linear combination as well. That whole thing could solve the differential equation. And again, this is for just the homogeneous ones, the equal to 0 ones. So this is why that linear independence is so important. If you find a bunch of smaller solutions, we can combine them into one big solution as long as they are linearly independent. All right, so here's one. y1, which is x squared, would solve this differential equation, right? And you can check it, right? I can say, all right, well, y1 prime is 2x, y1 double prime is 2. So let's plug y in there, y prime in there, oh, I need triple prime, that's a third. So I need a y1 triple prime, okay? That's supposed to be triple prime. This is again messy. And that's going to be 0, okay? So I plug them in here, here, and here, and I can see that this side's going to 0 out, so therefore this solves the differential equation. I could see whether or not this solves the differential equation. Where these come from, we're going to have to find out, but let's just say we already have them. I can see that this is also going to solve the differential equation, again, using everything that we did previously. I could find the derivative, the second derivative, the third derivative, and I could plug it in. Well, if each of these individually solve this homogeneous linear differential equation, then the combination of those things also, this whole thing also solves that same exact homogeneous differential equation. And this is ultimately the solution we want, because this solution has both the individual ones, but has the bigger combination as well. So this is what we're going to want to get to, and we're going to say that's the general solution to the homogeneous differential equation. All right? The trick is, well, where did these come from? How are we going to come up with those smaller ones? We'll build to that, right? We're just talking about the pieces right now of how we're going to build out the answer. The work of getting to those individual parts is the tricky part. All right, then we go into non-homogeneous. Okay, once we figure out, okay, all these little pieces, we got to figure out how to get them, but once we have all these little pieces, we can combine them into this general solution. How does that then help us find the non-homogeneous? Remember, because I just said a second ago, the homogeneous helps us solve the non-homogeneous. So then what we're going to say is, all right, this is where I was pointing out that the equal to 0 and the not equal to 0, look at the answers, right? So when I was doing this back in the linear lesson, I said, okay, let's look at the equal to 0 first orders. And we got one answer, and that one answer had, say, a C1 times some function, right? That's what our answer looked like. And when it was not equal to 0, okay, we got our solution to look like this. It had a C component, and then it had this other piece that didn't have a C component to it. So I said, you know, notice this. Does anybody remember me saying this when we did the linear lesson? Anyone remember me saying this? I said it about 10 times during that linear lesson. First order linear.
Yeah, I remember it.
Okay. This is where it comes into play. Because when we solve the non-homogeneous ones, the not equal to 0 ones, okay, there's going to be two parts to these answers. One part we're going to call y sub c. The other part we're going to call y sub p. And if we can find those two pieces, we can solve the non-homogeneous differential equation. Now, what are these two pieces? The y sub c piece is the piece that has these c values in it, which is going to be the solution to the associated homogeneous differential equation, okay? So we just said the linear combination of all the individual solutions to a homogeneous can be put together as one big solution. So if I look at a non-homogeneous differential equation and I want to solve it, let's say this one, the first thing I'm going to have to do is solve the associated homogeneous one. So set it equal to 0. And that's going to give me the y sub c. That's one part to my answer. That's sort of this one piece that has c's in it. Okay. Then I need to find this other part. This other part's called a particular solution. And that's going to be completely free of arbitrary C's, right? Notice this other piece didn't have any C's in it when we did it back for the first order. That same thing's going to follow suit. So then the second part to my answer has to be completely free of arbitrary variables. So I have to find what's called a particular solution to the differential equation. So we're going to have to come up with that. We'll be able to find this by solving the associated homogeneous. We're going to have to figure out a way to find this other part, this particular solution. But once we find both pieces, we'll put them together and we'll get the solution to the entire non-homogeneous differential equation. This is how we're going to have to build it. So if I look at this example here, and I said, let's try and solve this, in this case, third order non-homogeneous linear differential equation. Okay, again, categorizing these equations is important. Okay, third order because I have the third derivative and it's non-homogeneous, which is going to be a real important thing for us in this chapter. So let's say I could solve the associated homogeneous. If it was equal to 0, not 3x, but was equal to 0, I knew how to solve that. Let's just assume that. And I came up with this as the answer to the associated homogeneous. Okay. Well, that's part of what I need to solve the non-homogeneous. Then let's say I knew how to find a particular solution, which is a solution that doesn't have any C's in it. And I somehow came up with this. And that was a solution to the homogeneous, to this one, the 3x one. Okay. So let's say I knew how to come up with these two pieces. Well, then the solution as a whole big solution to this non-homogeneous would be both pieces added together. Okay. So that would give me this C1 e to the x plus C2 e to the 2x plus C3 e to the 3x, which again, we know all these are linearly independent. Okay, we've already determined that. That was one of the examples we did. Plus this other piece, which is negative 11 over 12 minus 1 over 2x. Combine those two parts. How we find them, that's what we need to learn. That's what this whole chapter is all about, is learning how to find these things. But if we knew how to find this piece and this piece, this comes from the homogeneous, this comes from the non-homogeneous, we put them together and that whole thing is one giant solution to this differential equation. Okay? So that's what I was talking about before. When it's not equal to 0, when we were doing the first orders, I said, notice there's two parts to our answer. There's a part that has C in it, in this case, multiple C's in it, and there's a part that doesn't have C in it, okay? So when we're solving these bigger ones, they're not first order anymore, they're third order, fourth order, whatever. The solution should still be built the same way. There should be two parts to the answer, the part that has the C's in it and the part that doesn't have the C in it. Y sub C is the part that has those C's in it, right? We'll call that the general solution to the associated homogeneous, or we're going to call that the complementary solution, which is why the C is there, Y sub C, complementary solution. And then we're also going to need the other part, which we call a particular solution, which is free of those arbitrary C values, arbitrary parameters. And we're going to have to come up with ways of how we do this. How do we find all these pieces? Well, once we learn how to find them, we now know how we're going to put them together to solve the differential equation, okay? And it matters whether or not it's homogeneous or non-homogeneous to start, whether we even have to go through all this, okay? If it's homogeneous to start with, we just need this one part. But if it's non-homogeneous to start with, we need that plus this other thing, okay, this Y sub P. Y sub P, particular solution, Y sub C, complementary solution, add them together, you get the whole solution, okay?